Okay, learning curve extrapolation. In order to understand this method, we should first understand what learning curve is. So let's remember what we were doing. There's a search space. Within that search space, the search strategy chooses an architecture. That architecture, for that architecture, we make a performance estimation. What is a performance estimation? You train that architecture from scratch. What is training? You feed some data, and by gradient descent or some other technique, most probably gradient descent, you wait for a couple of iterations or some epochs, number of epochs, you don't know, depends on your application, and you obtain a graph, a learning curve graph. Actually, you obtain a network and you obtain some accuracies on validation data, but along with that, you obtain a graph, which is called the learning curve. In order to show you what learning curve is, I've prepared some learning curves from some experiments we've done with Melis. Melis will recognize them. So when you're training something, you do a lot of experiments to find the correct hyperparameters. Actually, we've previously said that finding hyperparameters, searching for hyperparameters like the learning rate is similar to searching for an architecture, because architectures are, if you structure them correctly in a search space, are a set of parameters. Anyways, let's look at an experiment. This is an experiment. So in this experiment, we check the roots mean square error and also loss. Let's focus on the loss. Loss function is the function that designates your error. So your training sets error depending on the training label data, so the ground truth. So if you check in a couple of epochs, because we got 1,000 epochs, in 10 epochs or 20 epochs, the error falls, then it starts to fall very slowly, guys. Okay, it still falls, but it takes time for this guy to fall. So if this parameter set, we got this result. But with another training set, with the same parameters, for example, we got this kind of a result. If you check the loss, within a couple of epochs, the loss falls something to a value of 200. How this value is calculated depends on the type of loss. You could be using different types of loss. What is a loss in a deep neural network? Not the scope of this course, within the scope of the previous semester's course, but you can see that the loss decreases. The loss decreases means it is learning. So if you check it, in a couple of epochs, it falls to something 200. Something like 200. And if you check, this falls to 800 and just doesn't go well. So if you compare these two graphs, this experiment and this experiment is much better in the sense that it converges to a lower loss very quickly compared to the other experiment. Actually, in this method, what we are doing is we are checking a couple of epochs, 1 to 5 epochs, and check the curve and try to understand how the curve will continue, which is extrapolating that curve and saying, well, this one learns very fast, so this architecture must be good. So what we're doing is we feed an architecture, we train it for 5 epochs, get a curve, extrapolate that curve, and get a meaning, and try another architecture, train it for a couple of epochs, 5 epochs again, try to extrapolate that curve, try to understand how will the curve will be in future epochs. Then we decide. This way, we don't spend so much time in training all of the network for thousands of epochs. 5 epochs is enough for this speed-up method. So this is a possible way of estimating an architecture's performance using the learning curve extrapolation. For example, this paper, they propose a method for hyperparameter optimization. Actually, we just said that hyperparameter optimization is something similar to architectural search because you're searching for hyperparameters or some architectural parameters. They are all parameters. You're trying in a search space. So it's a similar problem. So what they do is they train it for some low number of epochs and they try to understand how the curve will be, and depending on the feature of that curve, they make an assumption. Okay, let's continue. They propose to extrapolate, these guys, this paper, propose to extrapolate the initial learning curves, and they terminate the operations for those experiments which does not converge, which perform poorly in the starting epochs. That will speed up the process, so you won't just lose time for some unwanted architectures. Well, of course there's a trade-off. Whenever you do an optimization, there is a trade-off, guys. The main challenge for predicting the performances of neural architectures is that in order to speed up the search process, good predictions in a relatively large-scale search space need to be made based on relatively few evaluations. So, okay, you're doing a few evaluations in this space, but what if in a couple of epochs you couldn't see the real nature of that training? That's the trade-off, and that's the trade-off you should take into consideration, but that's a speed up. Otherwise you won't be able to do the experiment. Now you can do the experiment. Okay, the next one, as you can see, we have covered these two, and this one, the next one. The third one is based on an idea which is called network morphism, guys. This approach is based on speeding up the performance estimation by using the weights of the architectures. But wait, this is a bit difficult thing, because we have an architecture here. Search strategy trains it. Then we have another architecture. If the architectures are different, how can we transfer the weights? Well, if you make the architectures having some parts which are overlapping on each other, you can just transfer the weights. So how to overlap them? How to transfer the weights when the architecture is different? One way of achieving this is by these guys. These guys are the guys who have proposed the idea of network morphism. It is actually a network starting from a very primitive network, a small network. It gradually grows, it morphs to a larger one. So how they achieve is they allow modifying an architecture while leaving a function represent the network unchanged. So you start with a little network, you train it, then in the next architectural search, you add layers on top of it, but freeze the layers which were inherited from the previous architecture. So you only train it for the outer layer, the appended, the new added layers. And just training for a new added layers is like fine-tuning a network, which will take much less time. So this way you just gradually grow, and you obtain, by morphing and growing morphing, you obtain an architecture in which for each performance estimation iteration you spend less time. So this results in methods that only require less GPU days. That's how it is done. So it's actually structural. Well, in this method, you increase the capacity of the network successively at each iteration. You start with a small network, then another network, then another network. So this way, you are always making the architecture bigger. That's the nature of it. So this idea is called the network morphism, guys. So continuing training for a few epochs can also make the use of additional capacity introduced by network morphism. This sentence tried to say that when you add a little part, you can only train for a few epochs and just transfer it for the next iteration. Well, it is advantageous because they allow search spaces without an inherent upper bound. It can go, so the search space is infinite, but it starts from a point. But the downside is this strict network morphism, the first idea proposed by these guys, VIII et al., which we have seen in the paper, VIII et al., these guys. In their idea of network morphism, the network always grows while morphing. But when you always make it grow, it will become very large after some time. If the network morphism worked in a way which would make the network grow and shrink at some periods, so just the structure of the morphing, if the structure of the morphing mechanism was more advanced, that would give us a better network because it would be going to infinity in size. Well, this can be attenuated by employing a method called approximate network morphism, which was proposed by these guys last year, it's a couple of months ago. Efficient multi-objective neural architecture search via this Lamarckian evolution. Actually, they use evolutionary methods as well. Their structure is called the lemonades. L standing for the Lamarckian evolution. So this is one of the very new ideas, guys. This is worth examining if you're interested in the subject. Okay, so this is how you do network morphism and how you do weight inheritance so that your performance estimation strategy becomes much faster. Okay, and the fourth one, as you can see, we had four different speed up strategies for performance estimation. We have come to the fourth one. Okay, let's see the fourth one in the next video.